Welcome back to my YouTube channel. Today we will discuss mean value theorems. Okay. Mean value theorems say that a function from closed interval a b to r which consists two properties. Function is continuous on closed interval a b and function is differentiable on open interval a b. Then there exists a c belongs to open interval a b such that f of a minus f of b equal to f dash c into b minus a. Okay, this is a statement of the mean value theorem. First of all, the mean value theorem explained in graphically. Okay, so this is x-axis. Okay, and this is y-axis. Suppose my point A here and B here, and this point is A comma f of A and this point B comma f of B. Okay, and the graph of the function this. Okay, or this is also called curve of the function. Okay, curve. Okay, so first of all we join the line segment this. Okay, so the mean value theorem say that there exists a point xi belongs to A and B or between A and B such that the tangent at the point xi comma f of xi is parallel to the line segment, this line segment, this. Okay, that is, this is my tangent here. Okay, this is parallel to the line segment this line segment parallel to the this tangent. So this is my xi. Okay, xi comma f of xi. Okay, this is xi. So xi lies between A and B. Okay, that means, so mean value theorems guaranteed that there exists xi between A and B such that the point xi comma f of xi at the point the tangent of the curve is parallel to the line segment joining the point A comma f of A and B comma f of B. That is say in graphically. Okay, now mathematically we can also prove. Now the proof of the mean value theorem. Now start the proof. Okay, let hx equal to f of x minus gx. Okay, and where gx equal to f of a plus f of b minus f of a by b minus a into x minus a. Okay, so clearly h is continuous because f of a and gx are continuous function, and also h is differentiable because f is differentiable and g is clearly differentiable function. Okay, on open interval a b. Okay, differentiable on open interval a comma b. Okay, and this is continuous on closed interval a comma b, hx. Okay, now h of a that equal to f of a minus g of a. Okay, so this equal to f of a minus, put the value x equal to a in this function of gx. We can give him, this is my called equation number 1. From 1 we gives f of a plus b minus a f of b minus f of a into a minus a. Okay, this is equal to 0. Okay, and this the product equal to 0. Okay, so this equal to f of a minus f of a, so this equal to 0. Okay, now find f of b, h of b. Okay, so this equal to f of a, f of b minus g of b. Okay, that is equal to f of b minus from 1 f of a plus from 1 this. Okay, replacing x equal to b only, so we can gives f of b minus f of a by b minus a into b minus a. Okay, so this equal to f of b minus f of a and plus f of b minus f of a. Okay, so actually this equal to f of b minus f of b. This is also equal to 0. So hence, so we have h of a equal to 0 equal to h of b. Okay, now applying Rolle's theorem on the function h. Okay, now by Rolle's theorem, there exists C belongs to A comma B such that h dash C equal to 0. So we consider hx equal to f of x minus g of x. So h dash x equal to f dash x minus g dash x. So this equal to, and also here gx equal to f of a plus f of b minus f of a by b minus a into x minus a. Okay, so g dash x equal to, this is constant value, so this is derivative equal to 0, and this is also constant, this is common term, and h is independent, h is variable, so here dx hx equal to 1, so this equal to f of b minus f of a by b minus a. Okay, now so put x equal to c, so we have h dash c equal to 0 from these two. This is equation number 2 from 2. So they put the value at x equal to c, so we can gives from here, so f dash c minus g dash c equal to 0. So this equal to, from here we have f dash c minus f of b minus f of a by b minus a equal to 0. So this equal to f of b minus f of a by b minus a equal to f dash c. Okay, and this equal to f of b minus f of a equal to f dash c b minus a, and hence the proof. Okay, and also the Rolle's theorem already discussed the previous lecture.